Imagine waking up one morning and stepping outside to find that the sky has changed forever. Not subtly, not in some way you might dismiss as a trick of the light or a passing cloud formation. The change is absolute, overwhelming. The kind of thing that stops you dead in your tracks, forces the air out of your lungs, and makes every rational thought you've ever had dissolve into pure, primal disbelief. You look up, and where the moon has always been, where that familiar silver disk has hung for every single night of your life, for every night in all of recorded human history, for every night since our earliest ancestors first looked up at the sky and wondered what was out there, something else is staring back at you. Something enormous. Something rust-colored and alien and terrifyingly, impossibly close. A world where a world should not be. Mars. The red planet. Right there. Hanging in your sky like a god that has decided to move in next door without asking permission. This is not a dream. This is not a hallucination. And it is absolutely not something you can just go back inside and pretend didn't happen. Because if Mars were suddenly placed where our moon is right now, if it occupied that same orbital slot, that same distance of roughly 384,000 kilometers from Earth's surface, the consequences would not be merely dramatic. They would be catastrophic in ways that most of us have never been equipped to imagine. And yet the question itself is irresistible, isn't it? What would actually happen? What would the sky look like? What would you feel standing on the surface of a world being torn apart? What would happen to the oceans, to the ground beneath your feet, to the delicate web of life that has taken 4 billion years to construct on this planet? What would happen to you? This is the kind of question that sounds like pure fantasy at first. A thought experiment for bored students or science fiction writers looking for a dramatic premise. But here is the thing that makes this question so much more than casual speculation. The physics behind it are completely real. The gravitational mechanics, the tidal forces, the atmospheric interactions, the orbital dynamics, all of it can be calculated with the same tools that astronomers and planetary scientists use every single day. And when you actually run those numbers, when you actually sit down and work through what the replacement of the moon with Mars would mean, the results are not just interesting. They are staggering. They are humbling. And in some cases, they are genuinely terrifying. So let's do this properly. Let's not just wave our hands and say things would be bad. Let's actually go there. Let's walk through it together, step by step, starting from the very moment of replacement and following the chain of consequences as far as it leads. Let's understand not just what would happen, but why it would happen, and what that tells us about the extraordinary fragility and the extraordinary resilience of the world we actually live in. Because this thought experiment, as wild and speculative as it sounds, has something profound to teach us about the real relationship between Earth and the Moon, about forces that operate on scales so vast and so ancient that we rarely stop to appreciate them. And it has something to teach us about Mars itself, a world that is simultaneously familiar and utterly alien, a world that has fascinated scientists and dreamers alike for centuries, and a world that, as we will discover, is in some ways far more dramatic than most people realize. Before we get to the moment of replacement, we need to understand what we're working with. We need to truly know both of the objects involved in this cosmic swap, because the contrast between them is itself one of the most revelatory aspects of this entire story. The moon that you know, the moon that has lit up lovers' walks and guided ancient sailors and inspired an almost incomprehensible quantity of poetry and mythology and religion, is a relatively modest object by planetary standards. It has a diameter of about 3,474 kilometers. Its mass is approximately 7.34 times 10 to the power of 22 kilograms. It's roughly 1/4 the diameter of Earth and about 1/81st the mass. It sits at an average distance of 384,000 kilometers from our planet's center, and it exerts a gravitational influence that is gentle enough that life on Earth has been able to evolve around it, to incorporate it, to depend on it in ways that are often invisible to us in our daily lives. Now consider Mars. Mars is a different beast entirely. Mars has a diameter of approximately 6,779 kilometers. That makes it nearly twice the diameter of our moon. Its mass is approximately 6.39 times 10 to the power of 23 kilograms. Do that comparison carefully. Mars is roughly 9 times more massive than our Moon. 9 times. Not 9% more massive. 9 times more massive. The difference between having the Moon in orbit around Earth and having Mars in orbit around Earth is not a subtle one. It is not a minor adjustment that our planet might shrug off. It is a transformation so fundamental that it would affect literally every system on Earth that we depend on for survival, and it would do so with a speed and a ferocity that would leave no aspect of life untouched. Think about what gravity means when you're talking about objects this size. Gravity is the fundamental force that governs the relationship between planets and their moons, between stars and their planets, between everything in the universe that has mass. And the strength of gravitational attraction depends on two things: the masses of the objects involved and the distance between them. Right now, the Moon pulls on Earth's oceans with a force that creates tides. Those tides rise and fall. They're impressive, certainly, if you've ever watched the sea come in or go out. In places like the Bay of Fundy in Canada, the tidal range can reach 16 meters. 16 meters of water rising and falling twice a day. That's already a powerful demonstration of what a relatively small moon can do to the oceans of a large planet. But now imagine replacing that moon with something 9 times more massive. The tidal forces scale with mass. More mass means more gravitational pull. More gravitational pull means bigger tides. And we're not talking about the tides getting a little bit higher. We're talking about something that would fundamentally alter the character of Earth's oceans, its coastlines, its geology, and its atmosphere. But let's not get ahead of ourselves. Let's start at the very beginning of this thought experiment. Let's start at the moment of replacement itself, because even getting Mars into that orbital position is an event worth dwelling on. How do we even conceptualize this? In the real universe, you cannot simply teleport a planet from one location to another. But for the purposes of this thought experiment, let's assume that some unimaginable cosmic mechanism has instantaneously placed Mars in the exact orbital position currently occupied by our Moon. Mars is now orbiting Earth at a distance of roughly 384,000 kilometers, completing one orbit every 27.3 days, just as the Moon does today. The Moon, for its part, has simply vanished, gone, removed from the equation. The first thing you would notice, if you happen to be standing outside at night when this occurred, is the sky. And what you would see in that sky would be something that no human being has ever seen before, and something that would immediately communicate to your most primitive, deepest instincts that the world has changed in a way that cannot be undone. Mars, at a distance of 384,000 kilometers, would appear in the sky as a disk approximately 3 times larger than the Moon appears from Earth. Think about that for a moment. Our Moon, which already seems impressively large when it's close to the horizon, already fills the sky with a presence that artists have painted and photographers have captured and dreamers have stared at for 10,000 years of civilization. That Moon would be replaced by something 3 times that size in angular diameter. Mars would subtend an angle of roughly 1.5 to 2 degrees across the sky, compared to the Moon's half degree. It would be enormous. It would be overwhelming. And it would be red. Not the pale, silvery white of the Moon you're used to. Not the gentle glow of reflected sunlight off gray rock and ancient craters. Mars is covered in iron oxide dust, in rust, and it would light up the night sky with a ruddy, coppery radiance that would be unlike anything in human experience. During a full phase, when Mars was on the opposite side of Earth from the Sun, it would be bright enough to cast shadows. Distinct, sharp-edged shadows. Imagine standing in a field at midnight and watching your shadow stretch out behind you, cast by the reddish glow of a planet hanging enormously overhead. The light would be different in quality from moonlight. Less silvery, more warm, more orange, more somehow ominous. Trees would cast red-tinged shadows. Snow would look almost pink. The ocean, when lit by this red giant moon, would look like something from another world entirely. But of course, the visual spectacle, as breathtaking and strange as it would be, is the least of our concerns. Because even in those first moments after the replacement, even before you've had time to properly process what your eyes are telling you, the physics would already be in motion. The gravitational dance between Earth and Mars would already be underway, and the first place that dance would make itself felt is in the oceans. Let's talk about tides, and let's be very clear about the mathematics here, because this is where things stop being awe-inspiring and start being genuinely frightening. The tidal force that a celestial body exerts on Earth is proportional to the mass of that body and inversely proportional to the cube of the distance between them. The cube. Not the square, the cube. This inverse cube relationship is crucial, because it means that tidal forces are incredibly sensitive to distance. A body that is twice as far away exerts tidal forces not twice as small, but 8 times as small. This is why the Sun, despite being much more massive than the Moon, actually exerts tidal forces on Earth only about 46% as strong as the Moon does, because the Sun is so incomparably far away. The Moon's closeness compensates for its small size. Now, Mars is roughly 9 times more massive than the Moon. And if we place it at the same distance from Earth that the Moon currently occupies, the tidal force it would exert would be approximately 9 times greater than what we currently experience from the Moon. 9 times greater. Stop and let that settle in. The Bay of Fundy, with its already stunning 16-meter tidal range, would experience tides not of 16 meters, but potentially of something approaching 150 meters. 150 meters. That's a wall of water rising and falling, twice a day, equivalent to a 40-story building. But this estimate, dramatic as it is probably conservative, because tidal phenomena are complex and can be amplified by coastal geography, resonance effects, and the interaction with existing ocean dynamics. The world's major coastal cities, London, New York, Mumbai, Tokyo, Shanghai, Sydney, all of them would be facing tidal forces so far beyond anything they were built to withstand that the concept of coastal infrastructure as we know it would become meaningless. But this is not just about flooding, though the flooding alone would be catastrophic beyond description. The real problem is not just the height of the tides. It's the energy. Tidal forces of this magnitude would pump enormous amounts of energy into Earth's oceans. They would drive currents of a power and speed that would dwarf anything that currently exists. The Gulf Stream, the Kuroshio Current, the Antarctic Circumpolar Current, all of these would be overwhelmed and restructured by tidal forces operating on a scale 9 times greater than today. The character of the global ocean circulation, which is the primary mechanism by which heat is distributed around the planet, which is responsible for keeping Western Europe warm enough to support dense human population, which feeds nutrients from the deep ocean to the surface where phytoplankton grow and produce roughly half of all the oxygen in Earth's atmosphere, that system would be fundamentally disrupted. Ask yourself this: if you removed the system that distributes heat around the planet, if you scrambled the ocean currents that regulate climate across entire continents, what do you think happens to the weather patterns that agriculture depends on? What do you think happens to the rain systems that fill rivers and aquifers? What do you think happens to the coastlines that nearly half the world's population lives within 50 kilometers of? These are not rhetorical questions. These are questions with answers, and the answers are deeply sobering. But we're still just getting started. Because the tidal effects of having Mars where the Moon is would not be limited to the oceans. One of the most profound and underappreciated aspects of tidal forces is that they act on solid rock just as much as they act on water. We just don't notice it as much because rock is solid and doesn't slosh around visibly. But Earth's crust actually flexes under the Moon's tidal pull. Right now, today, as you read this, the solid ground beneath your feet is moving up and down by about 30 centimeters with every tidal cycle. 30 centimeters of crustal flexing, happening invisibly, constantly, as the Moon passes overhead. You can't feel it because it's gradual and the whole ground moves together. But it's happening. With Mars in place of the Moon, that solid Earth tide would be amplified by the same factor of 9. Instead of 30 centimeters, the crust would be flexing by something on the order of 2 to 3 meters, twice a day. 2 to 3 meters of vertical movement in the solid rock beneath your feet. And this is not a gentle, slow, imperceptible movement anymore. This is a flexing of the lithosphere so significant that it would have dramatic consequences for the tectonic system. The plates of Earth's crust are already in motion, driven by convection currents in the mantle below. They grind against each other at fault lines, building up strain over years and decades until it releases in earthquakes. They subduct beneath each other, causing volcanoes. They spread apart at mid-ocean ridges, creating new seafloor. Now imagine adding a rhythmic, powerful, twice-daily mechanical stress to this already tense and dynamic system. Imagine the fault lines of the world, the San Andreas Fault in California, the Anatolian Fault in Turkey, the Cascadia Subduction Zone in the Pacific Northwest, the Himalayan Collision Zone, all of them being flexed and stressed twice a day by tidal forces 9 times stronger than those that operate today. The result would be a dramatic increase in seismic and volcanic activity. Not in every single earthquake being catastrophically more powerful, but in the frequency and energy of seismic events being significantly elevated. The geological record of Earth contains evidence of periods of dramatically increased volcanic activity called large igneous provinces, where vast quantities of magma erupted over relatively short geological timescales, sometimes triggering mass extinctions. The Deccan traps in India, the Siberian traps in Russia, events like these have been linked to some of the most dramatic biological crises in Earth's history. Increasing the tidal stress on Earth's crust by a factor of 9 would not necessarily trigger a large igneous province immediately, but it would fundamentally increase the energy input into Earth's tectonic system in a way that would make volcanic and seismic events significantly more frequent and potentially more intense. And here is something genuinely mind-bending to consider. The tidal forces from Mars would also be acting on Mars itself. The relationship between a planet and its moon is not a one-way street. Earth's gravity would be pulling on Mars with tremendous force, and just as the moon has been gradually receding from Earth due to tidal interactions, Mars would experience its own set of tidal stresses. Mars is already a geologically complex world. It has Olympus Mons, the largest volcano in the solar system, rising 22 kilometers above the Martian surface. It has Valles Marineris, a canyon system that stretches 4,000 kilometers across the Martian surface, large enough to cross the entire continental United States. Whether Mars has active geology today is a matter of ongoing scientific investigation. There is evidence from the InSight lander mission, which operated on Mars from 2018 to 2022, that Mars does experience Marsquakes, seismic events of varying magnitude. But if Mars were in orbit around Earth at the distance we're considering, Earth's tidal forces on Mars would be substantial, and the Martian geology might be significantly more active as a result. Now, let's talk about what happens in the sky during the day. Because while the nighttime view of a Martian moon hanging enormous and red overhead is dramatic, the daytime dynamics of a Mars-Moon system would be equally spectacular and equally consequential. Solar eclipses, when the moon passes between Earth and the Sun, are currently one of the most awe-inspiring natural phenomena that humans can experience. During a total solar eclipse, the moon covers the Sun almost perfectly, a coincidence made possible by the fact that the Sun is about 400 times the diameter of the moon, but also about 400 times farther away, making them appear almost exactly the same size in our sky. This is one of the most improbable and beautiful coincidences in all of astronomy. Mars would ruin this coincidence. Mars, being 3 times the angular diameter of the moon in our hypothetical sky, would cover the Sun completely during an eclipse, but not just barely. Mars would cover the Sun and a significant portion of the sky around it, creating a total eclipse with a corona visible around a much larger disk. The eclipse itself would be more total, more complete, and it would last longer. The shadow of Mars on Earth's surface would be enormous. Millions of square kilometers of Earth's surface would be plunged into darkness simultaneously, rather than the narrow path of totality, typically a few hundred kilometers wide, that we see today. This broader shadow would have measurable effects on temperature and atmospheric dynamics. But eclipses, as dramatic as they are, would be relatively infrequent events. The more continuous and consequential daytime effect would be the reflected sunlight from Mars illuminating Earth's surface. We've already touched on how bright Mars would be at night during its full phase. But what about during the day? During daylight hours, Mars would still be visible in the sky, a large, rust-colored disk that would be the most prominent object in the daytime sky after the Sun itself. On days when Mars was near the Sun, it might be difficult to see directly, but it would be there, and its presence would affect the psychology of every creature on Earth in ways we can only begin to imagine. How would animals that use celestial cues for navigation adapt? How would birds, sea turtles, monarch butterflies, all of which depend on the position of celestial objects for orientation, cope with an entirely different sky? The answer, almost certainly, is with great difficulty. Let's take a step back from the immediate physical consequences and ask a bigger question. What would happen to Earth's orbit? To its axial tilt? To the long-term stability of the planet's relationship with the Sun? These are questions that get into some of the deepest and most consequential aspects of planetary science, and the answers are critical to understanding the long-term fate of a hypothetical Earth-Mars system. Earth's axial tilt, the 23.5-degree angle at which our planet's axis is inclined relative to its orbital plane around the Sun, is responsible for the seasons. It's the reason why summer and winter exist, why the northern hemisphere is warmer when it's tilted toward the Sun and cooler when it's tilted away. Without this tilt, Earth would have no seasons. The tropics would be perpetually hot, the poles perpetually cold, and the temperate zones, where most of Earth's biodiversity and most of its agricultural land exists, would have a completely different climate regime. Now, here's something that most people don't know about the Moon's role in Earth's climate system. The Moon acts as a stabilizer for Earth's axial tilt. Without the Moon, computer models of Earth's orbital dynamics suggest that Earth's axial tilt could vary chaotically over time, potentially swinging from near zero to over 80 degrees over millions of years. Mars, we know for certain, has experienced such variations in its own axial tilt because it lacks a large stabilizing moon. Mars's axial tilt has varied by as much as 45 degrees over its history, driving massive climate swings that have dramatically altered its surface conditions repeatedly over geological time. So the question for our hypothetical scenario is, would having Mars as Earth's moon stabilize Earth's axial tilt? And the answer is deeply complicated. A more massive moon orbiting at the same distance would exert a stronger stabilizing influence on Earth's axis, all else being equal. So in that narrow sense, yes, a Mars-sized moon would actually provide more stabilization for Earth's tilt than our actual moon does. But there are other factors. The increased mass of the orbiting body would also affect Earth's orbital dynamics in more complex ways. The gravitational interaction between Earth, Mars, and the Sun would be a three-body problem of considerable complexity, and three-body problems in celestial mechanics are notorious for their potential to produce chaotic outcomes. While a somewhat stable orbit might be achievable in principle, the long-term dynamics of such a system would be more complex than the current Earth-Moon system, and there would be gravitational resonances and perturbations that could, over millions of years, lead to instabilities that our current Earth-Moon system does not face. There's also the question of what happens to the orbit of Earth as a whole around the Sun. Having a much more massive moon doesn't just mean Earth has a larger gravitational influence on its companion. It means the companion has a larger influence on Earth too. The Earth-Moon system actually orbits the Sun together, but they orbit around their common center of mass, called the barycenter. For the current Earth-Moon system, this barycenter lies inside Earth, about 4,600 kilometers from Earth's center, or about 75% of the way from Earth's center to its surface. But if you replace the Moon with Mars, the increased mass of Mars would shift this barycenter. With Mars 9 times more massive than the Moon, the barycenter would move significantly. It might actually move outside Earth's surface. This would mean that technically, Earth and Mars would orbit each other around a point in space between them, much more like a binary planet system than a planet-moon system. The distinction is significant. In a binary planet configuration, both bodies are of comparable importance in the gravitational dance, and the dynamics of the system are more complex and less stable than a simple planet-moon relationship. The gravitational implications of this shift in the barycenter would affect everything from Earth's orbital path around the Sun to the timing and character of seasons. Now let's turn to something that might seem more abstract, but is actually just as important as gravity and tides for the question of habitability: the atmosphere. Would Earth's atmosphere survive the presence of a Mars-sized moon? This question has several layers to it, and each layer reveals something interesting about planetary science. First, let's think about the direct effect of Mars's gravity on Earth's atmosphere. Atmospheric molecules at the very top of Earth's atmosphere can sometimes achieve escape velocity, the speed needed to break free of Earth's gravity and drift away into space. This process, called atmospheric escape, is constantly ongoing but extremely slow for Earth's current atmosphere. The reason is that Earth's gravity is strong enough to retain most of its atmospheric molecules, and the ones that do escape are the lightest ones, primarily hydrogen. Mars, by contrast, has a much weaker surface gravity, about 38% of Earth's, and has lost most of its original atmosphere over billions of years, partly through a process called atmospheric sputtering driven by the solar wind. If Mars is now orbiting Earth at close range, its gravity would be pulling on Earth's atmosphere. Not enough to strip it away dramatically, but there would be complex atmospheric interactions. The upper atmosphere would be distorted by the gravitational gradient between Earth and Mars. There could be tidal effects in Earth's atmosphere, similar to the oceanic tides but in the air, that would affect wind patterns, pressure gradients, and weather systems. There's a more dramatic atmospheric possibility to consider as well. Mars, even in its current depleted state, has a thin atmosphere consisting mainly of carbon dioxide, with some nitrogen and argon. If Mars were in close orbit around Earth, could gases transfer between the two worlds? The answer is yes, at least in principle, though the process would be extremely slow and complicated. More immediately relevant, Mars's thin atmosphere would interact with Earth's much denser atmosphere through electromagnetic and particle interactions. Mars currently lacks a significant global magnetic field, unlike Earth, which has a robust magnetosphere generated by its iron-nickel core. Earth's magnetic field protects our atmosphere from the solar wind, which is a stream of charged particles flowing constantly from the Sun. Without a magnetic field, Mars has been largely defenseless against the solar wind, which has contributed to the stripping of its ancient atmosphere. In our hypothetical scenario, Mars in close orbit around Earth would actually benefit from Earth's magnetic field, which extends far into space. Mars might find itself partially shielded by Earth's magnetosphere, which would be an interesting reversal of its current situation. But Earth's magnetosphere would also be affected by the presence of a massive conducting body like Mars orbiting within it. The interaction between Earth's magnetic field and Mars, particularly any remnant magnetic field that Mars might still have in certain regions of its crust, would create complex magnetospheric interactions. There would be electrical effects, possibly including spectacular aurora displays that would be far more extensive and energetic than the auroras we see today. The auroral displays might be visible not just near the poles but at much lower latitudes, potentially across large portions of the temperate zones. Imagine looking up on a clear night and seeing not just a rust-colored Mars dominating the sky but vast curtains of aurora rippling around it, green and blue and white light dancing in the upper atmosphere. The sight would be simultaneously magnificent and deeply unsettling. Let's pause here for a moment and ask a question that goes beyond the physics. Let's think about what this scenario means for life, for actual biological organisms. Not just for humans in our civilization, but for the entire web of life that has spent 4 billion years building itself into the complex, interconnected system that exists today. Would life survive? Would it adapt? Would some of it thrive even in these new conditions? Because life on Earth has survived some genuinely extraordinary challenges over its long history, and it is not without resources when faced with radical environmental change. The key question for life is not whether the initial disruption would be devastating. It almost certainly would be. The tidal forces alone would cause mass extinctions of coastal and marine species on a scale comparable to some of the great mass extinction events of Earth's geological past. The Permian-Triassic extinction event, the most severe extinction event in Earth's history, which occurred about 252 million years ago and wiped out an estimated 96% of all marine species and 70% of all terrestrial vertebrate species, was triggered by a combination of massive volcanic eruptions, ocean acidification, and global warming. The sudden appearance of a Mars-sized moon with 9 times the gravitational pull of our current moon would trigger disruptions potentially comparable in severity to the physical drivers of that event. Massive earthquakes and volcanic eruptions, globally disrupted ocean circulation, catastrophically altered weather patterns, dramatic flooding of coastlines and coastal habitats. The initial biological crisis would be severe and rapid, but life is resilient. Incredibly, stubbornly, defiantly resilient. After the Permian-Triassic extinction, life recovered. After the asteroid impact that ended the age of the dinosaurs 66 million years ago, life recovered. After the snowball Earth events that may have covered the entire planet in ice, life recovered. The question is not whether life would survive the initial disruption of a Mars-sized moon appearing. Some life certainly would. The deep ocean, buffered from surface chaos by kilometers of water, would provide refuge for some organisms. Inland areas far from coastlines and fault zones would experience less immediate disruption. Underground environments, caves, and deep soil ecosystems would continue functioning after a fashion. Life, once it had a foothold, would begin the long process of adapting to a dramatically altered world. And here is something fascinating to consider. The new tidal environment, while devastating for most existing life, might actually create some very interesting conditions for life in the long run. Extreme tidal environments on Earth today, places like salt marshes, tidal pools, and intertidal zones, are among the most biologically productive ecosystems on the planet. The constant cycling of water, the mixing of nutrients, the regular exposure and inundation, all of these factors create conditions that encourage biological innovation and productivity. With tides 9 times more powerful than today's, the intertidal zone would be vastly expanded. The area of coastline that experienced regular tidal flooding and exposure would be enormous. This might, over geological timescales, provide an extraordinary laboratory for evolutionary innovation. Different conditions drive different evolutionary solutions. Some of the most important evolutionary transitions in Earth's history, including the transition from aquatic to terrestrial life, may have occurred in intertidal environments. A world with dramatically amplified tides might be, paradoxically, an evolutionary engine of extraordinary power, even if the immediate disruption was catastrophic. Now let's take the thought experiment even further and talk about something that people rarely consider in these discussions. What the scenario would mean for the experience of time and the calendar. This might seem trivial compared to tides and earthquakes, but it's actually revelatory about how deeply the moon is woven into human civilization and into the biological rhythms of Earth's living systems. Our calendar is fundamentally lunar. The month, one of the most basic units of human timekeeping, is derived directly from the cycle of the moon. The word month comes from moon. The word menstrual comes from the same root, reflecting the approximately monthly cycle of human female fertility that evolved in sync with the lunar cycle. Many religious traditions use lunar calendars, including Islam, Judaism, and various Hindu traditions. The agricultural practices of countless human cultures have been organized around the lunar cycle, from planting times to harvest festivals. The tides themselves, which fishermen and sailors and coastal peoples have depended on since prehistoric times, run on the lunar cycle. A Mars-sized moon would maintain approximately the same orbital period as our moon, roughly 27 to 29 days depending on how you count, so the basic concept of a month would persist. But the character of that month would be dramatically different. The phases of Mars-Moon would follow the same pattern, waxing and waning through a cycle of about a month. But the full-phase brightness, the sheer overwhelming presence of a nearly full Mars hanging overhead, would be qualitatively unlike anything our current full moon produces. Many animals use lunar light as a cue for behavior. Grunion fish in California breed on specific nights following the full moon, using the tidal patterns and the moonlight as signals to synchronize their reproduction. Sea turtles use moonlight to navigate from their nesting beaches to the ocean. Coral reefs around the world spawn simultaneously, triggered by the combination of lunar phase and water temperature. Insects, birds, nocturnal mammals, all of these have behaviors tuned to the lunar cycle. With a Mars moon 9 times more reflective and 3 times larger in angular diameter in the sky, the intensity of light on even moonlit nights would be dramatically greater. A full Mars moon would be far brighter than our current full moon, potentially bright enough to significantly suppress the melatonin cycles of many organisms. Melatonin is the hormone that regulates sleep and circadian rhythms in many animals, including humans, and it is suppressed by light. A much brighter moon would mean darker, harder to achieve sleep for many organisms, disrupting circadian rhythms that have been calibrated over millions of years. And what about the night sky beyond Mars? One of the things that would be profoundly changed by having a much brighter, much larger Mars moon is the visibility of the stars. Our current moon, especially when full, already washes out many dimmer stars with its reflected light. With a Mars moon 3 times larger and significantly brighter, the area of sky contaminated by its light would be much greater. On nights when Mars moon was above the horizon, the faint stars of the Milky Way, the galaxies visible to the naked eye, the delicate tracery of dimmer constellations, all of these would be largely invisible. The night sky, which has been the canvas of human mythology and the inspiration of astronomy since our species first became curious, would be dramatically altered. Whether this is a gain or a loss depends on your perspective. You would gain a spectacular, overwhelmingly present planetary neighbor dominating your sky. You would lose the immense depth of the starry universe beyond it. Let's shift our attention now and think more carefully about Mars itself in this scenario, because in all the discussion of what Mars would do to Earth, we've somewhat neglected what Earth would do to Mars. And the answer is quite a lot. Earth's tidal forces on Mars, at this close range, would be enormous. Earth is about 10 times more massive than Mars. With Mars orbiting at 384,000 kilometers, Earth's tidal forces on Mars would be even more powerful than Mars's tidal forces on Earth, because tidal force scales with mass and Earth is more massive. The result would be intense tidal stress on the Martian crust and mantle. Mars, which is thought to have a partially molten or at least thermally active interior based on InSight data, might be significantly heated and activated by this tidal stress. Tidal heating is a real phenomenon. The most spectacular example in our solar system is Io, the innermost large moon of Jupiter. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes continuously erupting and reshaping its surface. This extraordinary geological activity is driven almost entirely by the tidal forces from Jupiter and the other Galilean moons, which constantly need Io's interior and generate heat through friction. Could Earth's tidal forces do something similar to Mars? Almost certainly not to Io's extreme degree, because Earth is much less massive than Jupiter and the geometry of the Mars-Earth system is different from the Io-Jupiter system. But there would be significant tidal heating of Mars, potentially reactivating geological processes that have been dormant for hundreds of millions of years. What would a tidally heated Mars look like? It might develop more active volcanism. Olympus Mons, the solar system's largest volcano, might become active again. The Tharsis volcanic plateau, which dominates one hemisphere of Mars, might see new eruptions. Valles Marineris might widen as the Martian crust is stressed and fractured by Earth's tidal pull. And here is something fascinating. Volcanic activity releases gases. On Earth, early volcanic activity is thought to have been crucial in building up the original atmosphere, releasing carbon dioxide, water vapor, sulfur compounds, and nitrogen from the interior of the planet. A tidally reactivated Mars might begin outgassing more intensely, potentially thickening its thin atmosphere over geological timescales. Not quickly enough to matter in human terms, not by a long shot, but over millions of years, A tidally active Mars might develop a denser atmosphere, potentially even liquid water on its surface, if the gases trapped in its interior were mobilized by the tidal heating. But there's a complication, and it's a significant one. Mars, at the distance we're discussing, would be subject to something called the Roche limit. The Roche limit is the distance from a planet within which tidal forces exceed the self-gravity of an orbiting body, meaning the planet's tidal forces can literally tear apart the orbiting object. For our Earth-Moon system, the Moon is well outside Earth's Roche limit, which for a rocky body of lunar density is approximately 9,500 kilometers from Earth's center. The current orbital distance of the Moon, 384,000 kilometers, is far, far beyond this limit. Mars, orbiting at the same distance, would also be well outside Earth's Roche limit. The Roche limit for a rocky body of Martian density would be somewhat different from the lunar calculation, but it would still be in the range of 9,000 to 12,000 kilometers. Mars at 384,000 kilometers would be safely outside this zone. So Mars would not be torn apart by Earth's gravity at this distance. However, and this is crucial, the tidal interaction between Earth and Mars would have long-term consequences for the orbit of Mars. Just as our Moon is currently slowly spiraling away from Earth, increasing in orbital distance at a rate of about 3.8 centimeters per year due to tidal interactions, Mars in this hypothetical scenario would either spiral inward or outward depending on the details of its rotation rate relative to its orbital period. Currently, our Moon is tidally locked, meaning it rotates once for every orbit it makes around Earth, so we always see the same face. This is because over billions of years, Earth's tidal forces slowed the Moon's rotation until it was synchronized with its orbital period. Would Mars be tidally locked in our hypothetical scenario? Not initially. Mars currently rotates once every 24 hours and 37 minutes, almost exactly the same as Earth's day. In our scenario, Mars would be orbiting Earth with a period of about 27 days, but rotating on its axis every 24 hours. This mismatch between rotation and orbital period would mean that Mars was not tidally locked, and Earth's tidal forces would be working to change that. The tidal forces would exert a torque on Mars, gradually slowing its rotation towards synchrony with its orbital period. This process would take an extraordinarily long time, probably hundreds of millions to billions of years, given the masses and distances involved. But during this gradual rotational deceleration, the tidal forces would be pumping energy into Mars's interior as heat. And on shorter timescales, the fact that Mars was not tidally locked would mean that different parts of its surface would periodically face Earth, creating a complex and dynamic tidal pattern in the Martian crust that would generate ongoing seismic and geological activity. Let's talk about something that is perhaps less obvious but deeply important. What happens to Earth's rotation? Right now, as a consequence of the tidal interaction with the Moon, Earth's rotation is gradually slowing down. The day is getting longer. Not quickly, not in any way that matters on human timescales, but measurably. The current rate of slowing is about 1.5 milliseconds per century. But over geological time, this is significant. We know that early in Earth's history, a day was much shorter, perhaps only 6 hours long. The fossil record of certain ancient tidal sediments, called tidalites, preserves evidence of the number of lunar months per year in the past, because tidal rhythms leave their signature in layered sedimentary rocks. Studies of these ancient tidal records suggest that about 500 million years ago, a day on Earth was about 21 hours long. As the Moon has gradually slowed Earth's rotation through tidal friction, the days have gotten longer and, correspondingly, the Moon has moved to a greater orbital distance, because the angular momentum that is removed from Earth's rotation is transferred to the Moon's orbit. With a Mars-sized Moon, this tidal braking effect would be much more powerful. 9 times more powerful, to use our rough estimate. Earth's rotation would be slowing dramatically more quickly. The days would be getting longer much faster. On geological timescales, Earth might reach a tidally locked state with Mars far more quickly than the Earth-Moon system would reach its own eventual tidal lock. Ultimately, if the system were stable for long enough, Earth itself might become tidally locked to Mars, always showing the same face to its giant companion, just as the moon always shows the same face to us. An Earth tidally locked to Mars would be a fundamentally alien world. One hemisphere would be in perpetual daylight from the sun, one in perpetual darkness, modulated only by the 42-day cycle of Mars's orbit around the sun as seen from Earth. The temperature extremes between the day side and the night side would be enormous. Winds of extraordinary speed would blow from the hot day side to the cold night side. Life, if it persisted at all, might cluster in a narrow twilight zone between the two extremes. Of course, all of this is speculative extrapolation over timescales of hundreds of millions to billions of years. Let's bring ourselves back to more immediate time frames and think about what the world would look like not in the far future, but in the months and years immediately following our hypothetical replacement event. Because the immediate consequences are dramatic enough without needing to extend our imagination into geological deep time. In the first hours after Mars appeared where the moon was, the most immediate life-threatening consequence would be the tidal surge. As we discussed, the tidal forces would be 9 times greater than those we currently experience. Tides are not just gentle risings and fallings of the sea. In some configurations, particularly when tidal energy is funneled into narrow bays or river estuaries, they become enormous, fast-moving walls of water. The Bristol Channel in England, with its already dramatic tidal range, would experience tidal surges that would be almost incomprehensible. The coast of Alaska, which has some of the world's most dramatic tidal ranges, would be similarly affected. But the most dramatic immediate effects would be felt not in these places of naturally amplified tides, but in coastal regions everywhere, because the baseline amplification of 9 times would make even normally modest tidal coastlines experience tide levels that would be considered extreme today. Consider, for example, New York City. New York currently has a tidal range of about 1.5 meters. 9 times that would be 13.5 meters. Manhattan, much of which is at very low elevation, would be repeatedly submerged as the Martian tides swept in and out. The subway system, the underground infrastructure, the basements of its towers, all would be flooded twice a day with every tidal cycle. The same would be true for London, where the Thames tidal range would go from 6 meters to 54 meters or more, easily overwhelming the Thames barrier and every other coastal defense system. For Mumbai, for Shanghai, for Miami, for Bangkok, for dozens of other major coastal cities, the situation would be similar or worse. The first tide after Mars's appearance would be a catastrophe of extraordinary magnitude, and it would not stop. It would repeat, twice a day, every day, without any possibility of adaptation or recovery in the short term. The earthquake activity would increase dramatically and quickly, not because earthquakes require time to build up, but because the added tidal stress would push fault zones that were already near their failure point over the edge. In the first days and weeks following the replacement, there would likely be a global wave of increased seismic activity, with earthquakes triggered along every major fault system on the planet by the suddenly amplified tidal loading. Some of these earthquakes would be among the largest in recorded history. They would trigger tsunamis that would compound the already devastating tidal flooding. They would trigger landslides in mountainous regions. They would damage or destroy infrastructure that might have survived the tidal flooding alone. The volcanic activity would take somewhat longer to respond, because the pathway from increased tidal stress to increased volcanic eruption involves the slow mechanical behavior of solid rock and partially molten magma, which operates on timescales of days to weeks rather than the near-instantaneous response of earthquake faulting. But in the weeks and months following the replacement event, an increase in volcanic activity would be expected, and some of that volcanic activity might be dramatic. The volcanoes of the Pacific Ring of Fire, the volcanoes of Iceland, of Italy, of Central America, of the Philippines, would all be operating in a higher stress tectonic environment. Some eruptions that might have been years or decades away in the normal timeline might be triggered ahead of schedule. And then there's the atmosphere. The immediate atmospheric effects of the replacement would include the disruption of global wind patterns by the altered tidal and gravitational environment. Weather systems that exist in delicate balance, driven by the interaction of solar heating, Earth's rotation, ocean temperatures, and topography, would be disrupted by the new gravitational and tidal regime. Storms might become more intense. Rainfall patterns might shift dramatically. The jet streams that govern weather in the middle latitudes might be displaced or fragmented. These atmospheric effects would be more diffuse and complex than the immediate tidal flooding and earthquake effects, but they would be no less consequential for the long-term survival of human civilization. Agriculture, which feeds 8 billion people and which requires relatively predictable climate patterns, would be in crisis within the first growing season. Crops planted based on centuries of accumulated knowledge about local climate patterns would face a climate that no longer matched those patterns. The disruption of ocean circulation, which regulates coastal temperatures and drives the rainfall patterns that most of the world's agricultural land depends on, would mean that some regions that were previously agricultural heartlands might receive much more or much less rainfall than before. The winter wheat of the Great Plains of the United States, the rice paddies of Southeast Asia, the wheat fields of Ukraine and Russia, the corn belt of the American Midwest, all of these enormously productive agricultural regions exist because of specific climate patterns that have made them suitable for particular crops. Those patterns would change, and changing them suddenly would mean food insecurity of an unprecedented scale. Now, let's think about this from a different angle. What would humans actually do in the face of this? And this is where the thought experiment becomes not just a physics exercise, but a profound meditation on human resilience, adaptability, and the way our civilization is organized. If you somehow knew this was going to happen, if you had any warning whatsoever, what could you do? The honest answer is, not very much to prevent the physical consequences, but potentially quite a lot to mitigate the human ones. You could move people away from coastlines. You could stockpile food. You could strengthen critical infrastructure. You could develop new agricultural strategies for changed climate conditions. But all of this would require an unprecedented level of global coordination, a willingness to make massive sacrifices in the present for future survival, and a social and political cohesion that human civilization has not historically demonstrated in the face of existential threats. The societal and psychological effects of seeing a huge, red, alien planet hanging in your sky every night would themselves be profound. There is a concept in psychology called solastalgia, the distress caused by environmental change in one's home environment, by the alteration of the landscape and natural world that you know. Philosopher Glenn Albrecht coined the term in the early 2000s to describe the feelings of grief and anxiety that people experience when their home environment is damaged or changed beyond recognition. The appearance of a Mars-sized moon in the night sky, the replacement of the familiar moon with an alien red world, would be the ultimate solastalgic event. The loss of the moon, of the familiar companion that has lit human nights for all of human history, would itself be a kind of grief. Many people would report feeling bereaved. The way people look at the sky, the way they relate to the night, to the dark, to the rhythms of the world, would all be fundamentally changed. Religiously and culturally, the effects would be staggering. The moon has sacred significance in virtually every human religious and cultural tradition. In Islam, the crescent moon is one of the most recognizable symbols. In Judaism, the calendar is lunar, and many of the most important religious observances are determined by the moon's phases. In many pagan and indigenous traditions around the world, the moon is a deity or a central spiritual figure. The loss of the moon and its replacement by a strange, enormous red planet would be interpreted by many as a sign of profound spiritual or religious significance. Some traditions would see it as an apocalyptic event. Others might develop new theologies centered on the red newcomer. The social and cultural disruption caused by this cosmic change would be enormous and unpredictable. Meanwhile, scientists would be working feverishly to understand the new reality. Astronomers and planetary scientists, suddenly faced with a new nearby world to study, would have access to a Mars that is 384,000 kilometers away rather than its current average distance of 225 million kilometers. The scientific opportunities would be extraordinary, even in the midst of catastrophe. With current telescope technology, a Mars at lunar distance would be visible in astonishing detail from Earth's surface. Features smaller than a kilometer across would be resolvable with large telescopes. The detailed geology of Mars, its surface history, its atmospheric chemistry, all would be observable in real time at an unprecedented level of detail. Robotic missions to Mars, which currently require 6 to 9 months of travel time, would require only a few days if Mars were orbiting at lunar distance. The scientific return would be enormous. Would humans attempt to land on Mars in this scenario? Given all the other crises occupying our civilization, it might seem absurd. But human curiosity is a powerful thing, and the temptation to explore a world hanging just a few days away by rocket would be immense. The challenge would be navigating the orbital mechanics of getting from Earth's surface to a body that is itself orbiting Earth, which would require some specific trajectory planning, but it would be vastly simpler than the real Mars missions we are currently planning. In this hypothetical world, humans might establish a presence on Mars within years rather than decades, and what they found there would depend on whether the tidal heating had awakened any geological activity on the red planet. This brings us to one of the most intriguing speculative possibilities of this entire thought experiment. Could a tidally heated Mars develop conditions more hospitable to life? We know that Mars once had liquid water on its surface. We know it once had a denser atmosphere. We know it has water ice at its poles and locked in its soil. The question of whether Mars ever harbored life is one of the most compelling open questions in planetary science. Several missions have found tantalizing hints. The Curiosity rover found ancient organic molecules in Martian rocks. The Perseverance rover has been collecting samples from an ancient lake bed that might have been habitable to microbial life billions of years ago. The InSight mission found that Mars is seismically active. Methane has been detected in Mars's atmosphere, though its source remains controversial. Life is one possible explanation for the methane, though geological sources are also plausible. In a scenario where Mars is placed in orbit around Earth and subjected to significant tidal heating, the possibility that any residual life, if it exists in Mars's subsurface, might be energized or awakened is genuinely interesting. Not that life would spontaneously appear, but that if life exists in Mars's deep subsurface, in hydrothermal environments or in briny aquifers, the tidal heating and the resulting geological activity might bring some of that life closer to conditions where it could be detected, or might even bring it to the surface. This is purely speculative, of course. We don't know if Mars has any life. But the scenario raises the fascinating question of what we might discover if we could actually examine a geologically active, tidally heated Mars from up close. Let's zoom out even further now and think about this scenario from the perspective of the entire solar system. The removal of the Moon from its current orbit and the placement of Mars in orbit around Earth would not just affect Earth and Mars. It would send gravitational ripples through the solar system. Mars's removal from its current orbit between Earth and Jupiter would change the gravitational balance of the inner solar system. The asteroid belt, which lies between Mars and Jupiter, is maintained in its current structure partly by the gravitational influence of Jupiter and partly by the other planets, including Mars. With Mars gone from its current position, the gravitational perturbations that currently kick asteroids out of the asteroid belt and occasionally send them toward the inner solar system would change. Over millions of years, this could significantly alter the rate at which Earth is struck by asteroids and comets. The other inner planets would also feel the absence of Mars from their gravitational neighborhood. Venus, which is in a gravitational dance with Earth and Mars, would have its orbit slightly perturbed. Mercury, the innermost planet, would be affected less directly. But over the very long timescales of orbital mechanics, the removal of a planet the size of Mars from its current position and its placement in orbit around Earth would alter the stability of the inner solar system. There are already existing computer models that suggest the inner solar system is only marginally stable over billions of years, with small probability of chaotic interactions between the planets. Removing Mars from its current orbit and adding its mass to the Earth system would change those stability calculations significantly. The Moon itself, if it was simply removed from existence rather than swapped to another location, would be gone. And its loss would have effects beyond just the Earth-Mars dynamics we've been discussing. The Moon's current gravity perturbs the orbits of near-Earth asteroids and helps keep certain orbital resonances stable. Its absence would allow some near-Earth asteroid dynamics to shift over millions of years. This is a reminder that the solar system is not a static, mechanical system where you can simply swap parts without consequence. Every object in the solar system is in a gravitational conversation with every other object, and changing any part of that conversation changes everything else, to varying degrees. Now, let's spend some time thinking about what the sky would look like from other perspectives. We've talked about what humans on Earth's surface would see. But what would an astronaut in orbit see? What would someone on the surface of Mars see? These are fascinating perspectives to explore. An astronaut in low Earth orbit, at an altitude of, say, 400 kilometers above Earth's surface, which is roughly the altitude of the International Space Station, would have a spectacular view of both Earth below and Mars in the sky above. The ISS orbits at about 7.7 kilometers per second, completing an orbit of Earth in about 90 minutes. From this vantage point, the astronaut would see Mars hanging enormously in the sky, much larger than it would appear from the surface, because the thin atmosphere of Earth at the surface slightly reduces the apparent size of distant objects. But more dramatically, the astronaut would see Earth below transformed. The tidal bulges in the ocean would be visible from orbit. Where major rivers meet the sea, vast plumes of disturbed sediment would be visible from space. The flooding of coastal areas would be visible from orbit as a thin band of turquoise spreading inland around every coast. During the night side pass, instead of the familiar city lights of Earth, there would be gaps where coastal cities had been flooded and darkened. And the massive Mars hanging in the sky above would dominate the visual field in a way that no previous astronaut has ever experienced. From the surface of Mars, things would be even more dramatic. An astronaut, or, in our hypothetical initial scenario, anyone who happened to be standing on Mars when it was moved into orbit around Earth, would find themselves with an astonishing view. Looking down, instead of seeing the Mars landscape stretching to the horizon under a pinkish sky, they would now see a view of Earth. But Earth seen from 384,000 kilometers away, which is exactly how far Mars is from Earth in this scenario, would look just like the Moon looks to us from Earth. It would be a blue and white disk about half a degree across in the Martian sky. Wait, no. From Mars's surface, the angular size of Earth would actually be larger than we see the Moon from Earth, because Earth is larger than the Moon. Earth would subtend an angle of about 1 degree in the Martian sky, appearing as a beautiful blue marble, clearly showing oceans and clouds and continents, going through phases just as the Moon goes through phases as seen from Earth. It would be the most magnificent object in the Martian sky, changing from a thin crescent to a brilliant full disk over the course of the month. But here's something extraordinary. From Mars, the gravity pulling the Martian explorer down toward Mars's surface would be the same 38% of Earth's gravity that current mission planners assume for future Mars colonists. The gravity from Earth, while enormous from Mars's perspective in terms of tidal forces, would be felt as an almost imperceptible gradient across the surface. The bulk of what you would feel on Mars's surface is still Martian surface gravity. So in a bizarre sense, a Mars colony in this scenario might actually operate much as planned in real Mars mission designs, at least in terms of the local gravity environment. But the psychological experience of looking up and seeing a full disk Earth, enormous and blue and cloud-swirled, dominating your sky every night, would be unlike anything any science fiction writer has imagined. It would be overwhelming, humbling, and it might, despite all the catastrophic consequences on Earth, inspire a profound sense of connection between the two worlds. Let's think now about the history of science and how the discovery of this scenario's mechanics would have changed the trajectory of human knowledge. One of the most important intellectual developments in the history of astronomy was the realization, driven by Newton's laws of gravitation, that the Moon's orbit around Earth and the fall of an apple to the ground are governed by exactly the same physical law. This insight, which Newton reportedly developed in part by thinking about the Moon as it related to terrestrial gravity, was the beginning of our understanding that the universe runs on mathematical rules that apply everywhere equally. The scenario of Mars replacing the Moon would make the power of gravity so visceral and immediate that the study of gravitation would have been inescapable from the earliest human cultures. You cannot ignore the gravitational effects of a body 9 times more massive than our current moon when those effects are manifesting as catastrophically altered tides, amplified earthquakes, and dramatic geological activity. The intuitive understanding of gravity as a force would be baked into every culture that developed under such a moon. The mathematics would follow more naturally, perhaps even sooner. Similarly, the question of what Mars is made of, and whether it might harbor life, would have been scientifically tractable from Earth in a way that our actual Mars is not. The fact that Mars orbits in our sky at the distance of our moon would mean that every advance in telescope technology would immediately yield spectacular new information about the planet. When Galileo turned his first primitive telescope to the sky in 1609, he observed the moon and saw craters and mountains. If Mars had been in the moon's position, Galileo would have observed a world with its own remarkable landscape, with Olympus Mons visible as a vast, slightly raised dome, with Valles Marineris as a dark slash across the equatorial region, with the polar ice caps clearly visible as white patches at the top and bottom. The scientific revolution in planetary science might have occurred centuries earlier than it did, driven by the astonishing detail available from a close, large planetary neighbor. But of course, the civilization doing that observing would itself have been shaped by millennia of living under a much more demanding and dramatic sky. Would such a civilization even survive to develop telescopes? The catastrophic consequences we've been discussing would not make the development of high technology easy. And yet, humans have shown an extraordinary capacity to develop complex technologies even under challenging conditions. The question of whether a civilization shaped by the Earth-Mars tidal environment would resemble our own, or whether it would be fundamentally different in its priorities, its values, and its scientific trajectory, is one of the most genuinely unknowable aspects of this thought experiment. Let's take a moment to appreciate the real moon for what it is, because one of the great gifts of this thought experiment is that it throws the actual moon into sharp relief. The moon is not just a pretty object in the night sky. It is a critical component of the Earth system, and its particular size, mass, distance, and composition have made it an ideal companion for a life-bearing planet. Think about what the moon actually does for Earth. We've talked about the tidal effects, and we've seen that a more massive moon would make those tides catastrophically more powerful. But the moon's current tidal influence is actually beneficial in some respects. The tides mix the oceans, preventing stratification. They drive nutrient cycling in coastal environments. They may have been important in the origin of life, by repeatedly wetting and drying tidal zones in a way that could have concentrated organic molecules and promoted the formation of protocells. The moon's size is just right for tides that are dynamic and biologically useful without being catastrophically destructive. The moon's role in stabilizing Earth's axial tilt is another example of its near-ideal properties. As we discussed, without the moon, Earth's tilt might vary chaotically. With the moon, Earth's tilt is maintained within a relatively narrow range, about 22 to 24.5 degrees over a cycle of about 41,000 years. This range of variation is small enough that Earth's climate has remained broadly hospitable to life throughout the moon's existence. The ice ages that have occurred over the past few million years, as dramatic as they appear in the geological record, are relatively mild climate variations compared to what Earth might experience with a chaotically varying axial tilt. The moon's reflective properties are also interesting. The moon is not actually very reflective by planetary standards. Its albedo, the fraction of sunlight it reflects, is about 12%. This low reflectivity means that moonlight, while sufficient to navigate by and beautiful to look at, is not so bright as to overwhelm the darkness of night and interfere with the ecological rhythms that depend on genuine darkness. Many creatures depend on truly dark nights for hunting, navigation, reproduction, and other behaviors. A more reflective moon, or a larger moon, might interfere with these dark-adapted behaviors. Mars, with an albedo of about 17%, would be somewhat more reflective than the moon, but not dramatically so. But its larger angular size in our hypothetical scenario would make it significantly brighter overall. And then there's the matter of the moon's formation. The leading theory for the moon's origin is the giant impact hypothesis, which proposes that early in Earth's history, Approximately 4.5 billion years ago, a Mars-sized body called Theia collided with Earth in a glancing blow. The collision ejected enormous quantities of material from Earth's mantle into orbit around Earth, and this material coalesced to form the Moon. Note the size reference. The hypothetical Theia body that created our Moon was approximately Mars-sized. So in a cosmic sense, Mars is not just the hypothetical replacement for our Moon in this thought experiment. Mars is something like the sibling of our Moon. The material that forms the Martian planet and the material that created our Moon came from the same population of planetary building blocks in the early solar system. There is something almost poetic in this relationship. The giant impact hypothesis is supported by multiple lines of evidence. The Moon's composition is very similar to Earth's mantle, as we would expect if the Moon formed from ejected mantle material. The Moon is relatively depleted in volatile elements, consistent with the high temperatures that would have been achieved in a giant impact. The Moon's orbital characteristics are consistent with formation from a disk of material ejected in a giant impact. And perhaps most tellingly, computer simulations of giant impacts with Mars-sized objects can reproduce the observed properties of the Earth-Moon system. When scientists run these simulations, they find that a body roughly the size of Mars, impacting Earth at the right angle and speed, produces a disk of material in orbit that would eventually accrete into a Moon similar to the one we actually have. So the thought experiment we've been running, while fantastical in its premise, is actually connected to real history. Mars, or something very like Mars, was involved in the formation of our Moon. The actual Moon is, in a sense, what happened after a collision with a Mars-sized body. And in another sense, the scenario we're exploring is asking, what if instead of a collision that mixed and melted and reformed material into our modest Moon, the Mars-sized body had simply parked itself in orbit? The answer, as we've seen, is chaos. Beautiful, terrifying, scientifically illuminating chaos. The Moon we have is not just an arbitrary satellite. It is the optimally sized, optimally distanced companion for a life-bearing planet. Too small, and its stabilizing and tidal influences would be diminished. Too large, and its gravitational influence would be catastrophically overwhelming. The Moon is, within the requirements of a habitable planet, something close to just right. This is not mysticism or fine-tuning argument. It's simply an observation about what kinds of planetary systems produce stable, long-term habitable conditions for complex life. Our Moon is part of what makes Earth special. This realization brings us naturally to the question of what other planetary systems look like, and whether there are other Earth-like planets in the universe with Moon-like moons. When we discover planets around other stars, which we do regularly now with instruments like the TESS Space Telescope and the data from the Kepler Space Telescope, we see an enormous diversity of planetary architectures. Some systems have massive planets very close to their star. Some have multiple planets in compact orbital configurations. Some have planets in highly elongated, eccentric orbits. The specific architecture of our solar system, with its gas giants far from the Sun and its rocky planets in the inner system, and with its Earth having a relatively large moon for a rocky planet, appears to be less common than some other configurations. This raises fascinating questions about the prevalence of life in the universe, and about whether having the right kind of moon is a prerequisite for complex life. The search for exomoons, moons orbiting planets around other stars, is one of the most active frontiers of astronomy. To date, the evidence for exomoons is suggestive but not conclusive. There are a handful of candidate exomoon detections, including a possible large moon around the exoplanet Kepler 1625b, detected by astronomers David Kipping and Alex Tichy. But detecting moons around distant planets is extraordinarily difficult, and the field is still in its infancy. The question of whether Earth-like planets commonly have moon-like companions remains open. Some theorists argue that large moons around rocky planets in the habitable zone of their stars might be relatively rare, because the specific combination of a Mars-sized impactor and a planet the size of Earth at the right distance and angle to produce a moon-sized moon is unlikely to occur frequently. Others argue that giant impacts are a natural consequence of planet formation, and that large moons around habitable zone rocky planets might be more common than we expect. These questions matter enormously for the search for extraterrestrial life. If a large, stabilizing moon is necessary for a rocky planet to maintain a stable axial tilt and thus a stable, hospitable climate for billions of years, then the Drake equation, the famous formula for estimating the number of technological civilizations in our galaxy, might need to include a term for the fraction of habitable zone rocky planets that have suitable moons. If that fraction is small, the universe might be lonelier than optimistic estimates suggest. If it's larger, the universe might be more richly populated with life. Let's come back to Earth now, literally, and think about some of the more subtle and perhaps surprising consequences of our Mars-Moon scenario that we haven't yet explored. One of the most interesting of these involves what scientists call the inner core of the Earth. Earth's internal structure consists of a crust, a mantle, and a core, which is divided into a liquid outer core and a solid inner core. The outer core, which is made mostly of liquid iron and nickel, is responsible for generating Earth's magnetic field through the dynamo effect, where the flow of electrically conducting liquid metal creates a self-sustaining magnetic field. This magnetic field, in turn, protects Earth's surface from the solar wind, a stream of charged particles from the sun that would otherwise strip away the atmosphere over geological timescales. The dynamics of Earth's liquid outer core are complex and sensitive to the planet's rotation rate and to any external forcing. We've established that a Mars-sized moon would exert tidal forces on Earth's solid body 9 times stronger than the moon currently does, and that this would cause the solid crust to flex much more dramatically. But the tidal forces would also act on the liquid outer core. The churning and convection of liquid iron in the outer core that generates Earth's magnetic field would be influenced by these amplified tidal forces. Whether this would strengthen or weaken the geodynamo, Earth's magnetic field generating engine, is difficult to predict without detailed modeling. But there is a real possibility that the dramatically altered tidal environment would affect Earth's magnetic field in significant ways. If the magnetic field were weakened or disrupted, even temporarily, the consequences for atmospheric retention and for the radiation environment at Earth's surface would be severe. Without the magnetic field's protection, the solar wind would begin to strip away atmospheric particles, as it does to Mars today. And without the magnetic field's deflection of cosmic rays and solar energetic particles, the radiation environment at Earth's surface would become significantly more hostile to life. But here's an interesting counterpoint. Some research suggests that tidal forces might actually help sustain the geodynamo by providing an additional energy source for the turbulent motions in the outer core. The question of what powers Earth's dynamo is still not fully resolved, and tidal effects are one of the proposed mechanisms. A Mars-Moon's amplified tidal forcing might actually make the geodynamo more robust, not less. This is the kind of nuance that makes planetary science genuinely difficult and fascinating. The system is so complex that even our best models leave significant uncertainties. Let's think about the seasons in a world with a Mars-sized moon. We've touched on the fact that Earth's axial tilt creates the seasons, and that a more massive moon would better stabilize that tilt. But there's another seasonal effect worth considering: the way a large moon influences the length and intensity of the seasons. Right now, the moon's gravitational influence on Earth is relatively subtle in terms of seasonal effects. The seasons are dominated by Earth's axial tilt and by Earth's slightly eccentric orbit around the Sun. But a Mars-sized moon would add its own gravitational complexity to Earth's orbit and rotation in ways that would create more complex seasonal patterns. The interaction of Earth's axial tilt, the Mars-Moon's orbital inclination relative to the ecliptic, and the gravitational perturbations of the Sun and other planets would create a climate system with more complex, less regular seasonal cycles than we currently experience. There would also be regular variations in the intensity of the tidal effects caused by the changing distance between Earth and Mars during Mars's slightly elliptical orbit around Earth. In the current Earth-Moon system, the Moon's orbit is not perfectly circular. It varies in distance from Earth between roughly 362,000 kilometers at perigee and 405,000 kilometers at apogee. This variation causes what we call supermoons, when the full moon coincides with the moon being at its closest point to Earth. In a Mars-Moon system, A similar variation in distance would cause tides of varying intensity, with the most extreme tides occurring when Mars was at its closest point to Earth. These extra-high supertides would be among the most dramatic regular natural events in the lives of Earth's inhabitants. Now I want to spend some time on a question that has haunted this entire discussion, a question that feels almost too large to ask, but that is impossible to avoid. Could life have originated on Earth in the first place if Mars had been where the Moon is since the beginning? This is one of the most profound counterfactual questions we can ask, because it touches on the deepest mysteries in science, the origin of life itself. The origin of life on Earth is still one of the great unsolved problems of science. We know it happened roughly 4 billion years ago, because the oldest evidence of life in the geological record dates to approximately 4 billion to 3.8 billion years ago. We know that life requires certain conditions: liquid water, a source of chemical energy, organic molecules as raw materials, and some mechanism for the self-replication and inheritance of molecular information. Beyond that, the specific environment in which life first arose is a matter of intense debate and ongoing research. Several hypotheses have been proposed for life's origin. One of the most compelling current hypotheses is that life arose in hydrothermal systems, either at deep-sea hydrothermal vents or in shallow, geothermally active surface pools like the kind Darwin suggested when he wrote about a warm little pond. Another hypothesis, championed by chemists like John Sutherland at Cambridge, suggests that life arose in a specific environment where UV light, water, and various minerals reacted to produce the complex organic molecules needed for life. Yet another hypothesis, panspermia, suggests that life arrived on Earth from space, carried by meteorites or comets. The tidal pool hypothesis for the origin of life is particularly relevant to our thought experiment. This idea, which has been developed by researchers including Charles Lineweaver and others, proposes that the rhythmic wetting and drying of tidal pools by the Moon's tidal action created an ideal environment for the concentration and polymerization of organic molecules. The cycle of wetting, which brings in new chemicals from the sea, and drying, which concentrates those chemicals and allows reactions to occur, might have been crucial for the emergence of self-replicating molecules. Studies published in journals like Nature Chemistry have explored how RNA, one candidate for the first self-replicating molecule, could be synthesized in conditions consistent with tidal pool environments. If the Moon was crucial for the origin of life, then having a Mars-sized moon with 9 times the tidal force would amplify those tidal cycles dramatically. Would this make the origin of life more or less likely? The answer is not obvious. More powerful tides would create larger, more dynamic tidal zones, potentially providing more area for the chemistry of life's origin to occur. But more powerful tides might also be too destructive, washing away concentrations of organic molecules before they could react to form more complex structures. The right amount of tidal cycling for life's origin might be moderate, not overwhelming. The Moon's tidal influence on early Earth might be close to optimal, just as its current influence is beneficial rather than catastrophic. This is a deeply humbling thought. Not only does the Moon's current size and distance seem well suited to supporting complex life now, but the Moon's historical influence on early Earth may have been part of the mechanism that started life in the first place. The Moon is not just an incidental feature of our planet's environment. It may be intrinsic to the story of life on Earth from the very beginning. Let's take a step into the realm of genuine speculation, clearly labeled as such, and ask a question that is perhaps the most mind-bending of all. What if there were life on Mars, and the placement of Mars in orbit around Earth resulted in that life being transported to Earth? This is genuine science fiction territory, and we want to be clear that this is a speculative scenario building on what we know about life's potential on Mars, not an established scientific claim. We know that Mars has, in its past, had liquid water. We know it had a denser atmosphere. We know it was potentially warmer. Multiple Mars missions have found evidence of ancient, water-rich environments that could, in principle, have supported microbial life. The question of whether Mars actually had life, or still has life in its subsurface, is one of the most exciting open questions in all of science. Assuming for the sake of speculation that Mars does harbor some form of microbial life, perhaps in protected hydrothermal environments in its deep subsurface. What would happen when Mars was placed in orbit around Earth at a distance of 384,000 kilometers? First, the increased tidal heating of Mars might activate geological processes that bring that microbial life closer to the surface. Hydrothermal systems might become more active. Subsurface liquids might be brought to the surface. The environment of Mars might become, in some localized areas, more hospitable to surface or near-surface life. But what about the transfer of life between planets? In real planetary science, there is a concept called lithopanspermia, the idea that life can be transferred between planets via meteorites. When a large asteroid or comet impacts a planet, it can eject material from the planet's surface at speeds exceeding escape velocity, sending rocks into space. These rocks can travel through the interplanetary medium for thousands to millions of years before potentially impacting another planet. We know that this process happens because we have found on Earth meteorites that originated from both Mars and the Moon. These Martian meteorites were ejected from Mars by impacts and eventually reached Earth. And in the other direction, Earth rocks have certainly been ejected by impacts, and some of them have reached Mars. If Mars were in orbit around Earth at lunar distance, the exchange of material between the two worlds would be dramatically amplified. Any impact on Mars, or any geological eruption that ejected material above Mars's escape velocity, would result in debris that would be orbiting in the Earth-Mars system. Much of this debris would, over time, fall to Earth. The exchange of rocks, and potentially any microbial life hitchhiking on or inside those rocks, between Earth and Mars would be dramatically more frequent than in the current solar system configuration. The question of whether microbial life could survive the journey, which would now be a matter of days rather than millions of years, is more tractable in this scenario. Short travel times would mean less exposure to the radiation of space, less time in the vacuum and cold, better chances for survival. Life in this hypothetical system would have a realistic pathway between the two worlds. This opens up what might be the most extraordinary possibility in this entire thought experiment. Could life from Mars and life from Earth interact? Could Martian microbes, arriving on Earth in meteoritic material, find a hospitable environment? Could Earth microbes, similarly transported, take hold on Mars? We have no idea whether Martian life, if it exists, would be based on the same chemistry as Earth life. If Martian life uses different molecular building blocks, different genetic chemistry, a different cellular architecture, it might be unable to interact with Earth life at all, unable to infect it, compete with it, or cooperate with it. But if Martian life is similar enough to Earth life, the implications of regular cross-contamination between the two biospheres would be extraordinary. Life on Earth and life on Mars might begin to share genetic information via horizontal gene transfer. Earth microbes might colonize habitable niches on Mars. Martian microbes might colonize Earth. The two biospheres might merge, producing a combined biological system unlike anything that has ever existed. This is pure speculation, clearly. We don't know if Mars has life. We don't know what form it would take if it did. We don't know whether the exchange of material we're describing would actually result in viable life transfer. But the possibility is scientifically grounded enough that astrobiologists take the question of planetary contamination very seriously in planning real Mars missions. The planetary protection protocols that govern actual Mars exploration are designed specifically to prevent contamination in both directions, preventing Earth microbes from reaching Mars and confounding the search for Martian life, and preventing potential Martian life from reaching Earth before we understand what it is and how it might interact with Earth's biosphere. In our hypothetical scenario, all such protocols would be moot. The two worlds are already in such close proximity that material exchange is inevitable. The biological story of this hypothetical solar system might be more complicated, more interconnected, and more surprising than anything we can easily imagine. Now let's think about something that we've not yet fully explored, the long-term orbital fate of this Earth-Mars system. In celestial mechanics, the stability of an orbital system over geological timescales is not something you can assume. You have to actually calculate it, or at least assess the relevant parameters. And the Earth-Mars system at lunar distance would have some significant stability concerns. One of the key questions is whether the orbit of Mars around Earth would be stable over billions of years, or whether it would decay, causing Mars to spiral inward toward Earth, or expand, causing Mars to move outward and potentially escape Earth's gravitational hold. In the current Earth-Moon system, as we mentioned, the Moon is gradually moving away from Earth. The mechanism is tidal friction. Earth's rotation is slightly faster than the Moon's orbital period, which means the tidal bulge that Earth's gravity raises on the Moon, and the corresponding tidal bulge that the Moon raises on Earth, are slightly misaligned. This misalignment transfers angular momentum from Earth's rotation to the Moon's orbit, causing Earth to spin down slowly and the Moon to move outward slowly. In a Mars-Moon system, the same physics applies, but the details would depend on the specific rotation rates and their relationship to the orbital period. If Earth is rotating faster than Mars's orbital period, the tidal interaction would transfer angular momentum from Earth to Mars, slowing Earth's rotation and moving Mars outward. If Mars's orbit expanded sufficiently, it might eventually reach a distance where Earth's gravity could no longer hold it, and Mars would escape. This would be the end of the Earth-Mars system. The specific timescale for this, if it occurred, would depend on many details of the tidal physics, but it could be on the order of billions of years, not millions. So in a human, or even a civilizational timescale, the orbit would be essentially stable, even if its long-term fate was uncertain. Alternatively, if for some reason Mars were rotating more slowly than its orbital period, the tidal interaction would drain angular momentum from Mars's orbit, causing it to spiral inward toward Earth. An orbit that decayed toward Earth would eventually approach the Roche limit, the distance within which tidal forces could tear Mars apart. As we calculated earlier, the Roche limit for a rocky body of Martian density orbiting Earth is somewhere around 9,000 to 12,000 kilometers from Earth's center. If Mars were to spiral inward to this distance, it would begin to be torn apart. Material would be stripped from Mars, forming a ring around Earth similar in some ways to Saturn's rings. Over time, the rest of Mars would either be pulled apart completely, raining debris down on Earth in a catastrophic bombardment, or it would impact Earth directly. A Mars-Earth collision, if it occurred, would be one of the most dramatic events in the history of the solar system. An object 9 times the mass of the Moon impacting Earth at orbital velocities would release an amount of energy roughly comparable to the original giant impact that is thought to have created the Moon. Earth's surface would be completely resurfaced. The entire crust might be melted. Vast quantities of material would be ejected into Earth orbit, potentially forming a new Moon. The consequences for any life on Earth would obviously be total extinction at the surface, though deep subsurface life might conceivably survive. It would be a full-scale reset of the Earth system, perhaps comparable to the Hadean period of Earth's early history immediately following the giant impact that created our Moon. Let's step back from this extreme endpoint and return to something more immediate and human-scaled. Let's think about the light that this thought experiment sheds on our current moment in history, on the real questions that scientists and space agencies are grappling with right now as we prepare to actually send humans to Mars for the first time. One of the most striking things about this thought experiment is how vividly it illustrates the relationship between orbital mechanics, planetary mass, and habitability. When we talk about sending humans to Mars in the real world, we often focus on the challenges of getting there. The 6 to 9 month travel time, the radiation exposure during the journey, the need to carry everything needed for life support. But one of the profound challenges of actually living on Mars, which is often underappreciated, is the difference in gravitational environment. Mars has 38% of Earth's surface gravity. This lower gravity has profound implications for human physiology. On Earth, our bones, muscles, cardiovascular system, and many other physiological systems have evolved to operate in a 1G environment. Space medicine research has shown that even the relatively modest transition to zero gravity in orbit causes significant physiological changes. Bone density loss, muscle atrophy, cardiovascular deconditioning, visual impairment due to fluid shifts in the body. Mars's gravity, at 38% of Earth's, is better than zero gravity but still significantly different from Earth's. The long-term health implications of living in 38% gravity are genuinely unknown. We have no data on long-duration exposure to partial gravity in the range of Mars's gravity. All our data comes from either zero gravity in orbital space or 100% gravity on Earth. In our hypothetical scenario, the humans on Earth would not be experiencing Mars's gravity, of course. They would still be on Earth under normal 1G conditions. But the thought experiment does illuminate the real challenge that Mars's gravitational environment poses for colonization. One of the most speculative but frequently discussed ideas for making Mars more Earth-like is terraforming. Transforming Mars's atmosphere, surface, and potentially even its rotation and gravity to make it more habitable for Earth life. Terraforming Mars is genuinely discussed by serious scientists, though it is currently far beyond our technological capability and would require centuries or millennia to accomplish even with perfect technology. But the most intractable problem with terraforming Mars is precisely the problem our thought experiment highlights. Mars's gravity is too low to retain a dense atmosphere over geological timescales. Even if you gave Mars an Earth-like atmosphere tomorrow, it would slowly be stripped away by the solar wind, because Mars lacks the magnetic field to protect it and lacks the gravity to fully retain it. To truly make Mars habitable long-term, you would need to address this fundamental problem. Our thought experiment provides an interesting, if extreme, solution to this problem. If Mars were in orbit around Earth, it would be protected by Earth's magnetic field, which extends far into space through the magnetosphere. And the tidal heating from Earth might reactivate Mars's own internal dynamo, potentially regenerating Mars's own magnetic field. It would not solve the lower gravity problem, but it might address the atmospheric stripping problem. A Mars in orbit around Earth, protected by Earth's magnetosphere and geologically active from tidal heating, might slowly rebuild a denser atmosphere over geological timescales. This is purely speculative terraforming, of course, and the other catastrophic consequences of having Mars at lunar distance would make this particular benefit irrelevant for any practical purpose. What this line of thinking does illustrate is that the environmental context of a planet matters enormously for its habitability. Mars, in isolation in its current orbit, is a cold, dry, largely airless world with hostile radiation and no liquid water on its surface. Mars in orbit around a large, magnetically shielded, geologically active Earth would be a fundamentally different world over geological time. Environment shapes habitability. Context is everything. This is a lesson that applies not just to planets but to every system in science and in life. Let's now explore the cultural and historical dimension of this thought experiment. Throughout human history, the moon has been a constant companion, a reference point for timekeeping, agriculture, navigation, mythology, and art. Virtually every human culture has developed a rich relationship with the moon, from the ancient Sumerian moon god Nana to the Greek goddess Selene to the Chinese moon goddess Chang'e to the Aztec moon deity Tequisistecatl. The moon's regular, predictable cycle, waxing and waning through its phases every 29.5 days, has served as one of humanity's oldest calendars. The Islamic calendar is still purely lunar. Many of the world's major religious observances, from Easter to Ramadan to Diwali, are set by the lunar calendar. The moon is woven into the fabric of human culture, religion, and timekeeping in ways that are so deep they are nearly invisible precisely because they are so pervasive. What would human culture look like if instead of the gentle, silver moon, our sky had always been dominated by a vast, rust-colored Mars? The mythologies would be different in ways that go beyond the surface replacement of one deity with another. The quality of the light, the character of the night, the behavior of the tides, the seasonal patterns that shape agricultural practices, all of these would be different, and each difference would cascade through culture in ways that are impossible to fully trace but are clearly enormous. The color red has a powerful psychological significance across many cultures. Red is associated with blood, with fire, with danger, with passion. If the dominant feature of the night sky were a large, red disk, the symbolic associations of red in human mythology and culture might be even more pronounced than they already are. Red might be the color of the sacred, of the cosmos, of divinity, in a way that blue or silver or white might be in a culture that looks up and sees our actual moon. The aesthetics of night, the emotional tone of darkness lit by a reddish glow, the character of shadow and moonlight in a world where moonlight is orange-red rather than silver-white, all of these would shape art and literature and music in ways that would make that world's creative output fundamentally different from ours. Science might have developed differently too. The moon has been one of the primary motivations for some of the most important advances in science. The debate over whether Earth or the moon was the center of the solar system, the development of Newton's laws of gravitation motivated in part by the puzzle of the moon's orbit, the development of tidal theory, the Apollo program that proved humans could travel to other worlds, all of these are examples of the moon driving scientific progress. With Mars in the moon's place, some of these same scientific questions would still arise, perhaps in more urgent form. The gravitational dynamics of a Mars-Moon system would be more complex and more obviously powerful, possibly motivating earlier and more intense study of celestial mechanics. The question of whether Mars harbored life, visible in such spectacular detail through even modest telescopes, would have been a central preoccupation of astronomy from its earliest days. And the Apollo equivalent in this hypothetical history, the first human landing on the Mars moon, would be perhaps the most dramatic event in human history, even more than the real Apollo 11 was. Traveling to a world that was so much closer, that was so visually prominent in the sky, that was clearly a planet with its own complex geology and possibly its own history of water and life, would have been an even more powerful cultural moment than the moon landings were. The images of astronauts standing on the surface of Mars, with Earth hanging enormous and blue in the Martian sky above them, photographed through the thin but slightly thicker than real Mars atmosphere of a tidally reactivated Mars, would be images of almost incomprehensible power and beauty. Now let's spend some time on the mathematics of how we actually know all this, because one of the things that makes this thought experiment so grounded and interesting is that it is not just speculation. The physics behind every consequence we've described is well understood and quantifiable. Let's walk through some of the key calculations, not in a way that requires advanced mathematics, but in a way that shows the logic and the real scientific foundation. The tidal force. We keep coming back to this, and with good reason. The tidal force is the difference in gravitational pull between two sides of a planet. If the near side of Earth is closer to the moon, it feels a stronger gravitational pull toward the moon than the far side of Earth does. This difference in pull is what stretches Earth into a slightly football shape, with tidal bulges on both the near and far sides. The mathematical formula for tidal force is proportional to the mass of the tidal body divided by the cube of the distance. If Mars is 9 times the mass of the moon and placed at the same distance, the tidal force is 9 times as strong. This is the core quantitative claim of our discussion, and it follows directly from Newton's law of gravitation. There's no uncertainty in this. It's physics. The Roche limit calculation is also straightforward. The Roche limit is approximately 2.5 times the radius of the primary body, Earth in our case, times the cube root of the ratio of the primary's density to the satellite's density. Earth's radius is about 6,370 kilometers. Earth's density is about 5,500 kilograms per cubic meter. Mars's density is about 3,900 kilograms per cubic meter. Plugging in these numbers, the Roche limit for a body of Martian density orbiting Earth is approximately 9,300 kilometers from Earth's center, well inside the 384,000 kilometer orbital distance of our hypothetical Mars moon. So Mars would not be torn apart. The orbit is physically stable on the mechanical level. The angular size calculation is also simple. The moon's diameter is 3,474 kilometers, and it's about 384,000 kilometers away, giving an angular size of about half a degree. Mars's diameter is 6,779 kilometers, roughly twice the moon's diameter. At the same distance, it would appear twice as large in angular terms, subtending about 1 degree of arc across the sky. This is a disk that would be clearly, dramatically larger than the moon appears to us. For reference, the sun also subtends about half a degree, so Mars would appear about twice the size of the sun and twice the size of our moon. Eclipses would be total and dramatic. The brightness of Mars as a moon is also calculable. The apparent brightness of an object in the sky depends on its angular size, its albedo, and the amount of sunlight falling on it. Our moon, with its 12% albedo and half-degree angular diameter, reaches a maximum apparent magnitude of about -12.7 at full moon. Mars, with a 17% albedo and twice the angular diameter, hence 4 times the angular area, would reflect roughly 4 times as much light times the small albedo correction, reaching an apparent magnitude potentially around -13.5 or -14. This would make the full Mars moon about 2 to 3 times brighter than our full moon. This might seem surprisingly modest given how much larger Mars would appear, but remember that the moon's 12% albedo means it's not very reflective. A brighter full Mars moon would cast noticeably more powerful shadows than our moon does, but it would not be bright enough to read by easily, though you might be able to with some effort. Now let's think about something that combines the physical and the philosophical. The concept of the habitable zone and what our thought experiment tells us about the conditions for life in the universe. The habitable zone, sometimes called the Goldilocks zone, is the range of distances from a star at which a planet could potentially have liquid water on its surface. Earth is in the habitable zone of our Sun. Mars is at the outer edge of the habitable zone. Some argue slightly beyond it. The concept of the habitable zone is a useful starting point for thinking about where life might exist, but it is increasingly recognized by astrobiologists as incomplete. A planet's habitability depends not just on its distance from its star, but on its mass, its geological activity, its atmospheric composition, its magnetic field, its axial tilt, and, crucially, the nature of any moons it might have. Our thought experiment illustrates dramatically why moons matter. The presence or absence of a moon, and the specific size and distance of that moon, can make the difference between a planet that supports complex life and a planet that is geologically and oceanographically chaotic and inhospitable. This is why some astrobiologists have proposed that the search for extraterrestrial intelligence should focus not just on planets in the habitable zone, but on planets in the habitable zone that also have large, stabilizing moons. This is a more restrictive criterion, and it would reduce the estimated number of potentially habitable worlds in the galaxy. But it might be a more accurate reflection of the real requirements for complex life, given what we know about the moon's role on Earth. The flip side of this argument is also interesting. Our thought experiment with Mars's moon shows that a moon that is too large can be catastrophic. A habitable zone planet with a moon-sized moon is probably better for life than a habitable zone planet with a Mars-sized moon. But a habitable zone planet with no moon at all might also be problematic, because of the axial tilt instability we discussed. This suggests that there might be a sweet spot of moon size for planetary habitability, large enough to stabilize the planet's axis and provide useful tidal mixing, but not so large as to overwhelm the planet with catastrophic tidal forces. Our moon appears to sit in this sweet spot, and the probability of landing in this sweet spot by chance might be part of what makes Earth special among planets, and part of what might make life like ours rare in the universe. Let's think about water. Water is life, as the saying goes, and in the context of our thought experiment, the behavior of water is absolutely central. We've discussed the dramatic amplification of ocean tides. But let's think more specifically about what happens to Earth's water in a Mars-Moon scenario over longer timescales. One of the consequences of dramatically amplified tidal forces and the associated increased geological activity would be changes in the water cycle. Stronger tides would drive more vigorous ocean mixing. More mixing would change the distribution of heat, salt, and nutrients in the ocean. The increased geological activity, specifically more volcanism, would also add more carbon dioxide and other gases to the atmosphere, potentially affecting the greenhouse effect and Earth's surface temperature. More carbon dioxide means more warming, which means more evaporation, which means more water vapor in the atmosphere, which means more rainfall. But whether that rain falls in places currently dry or in places currently productive of crops, and whether the changes in ocean circulation reinforce or counteract the greenhouse warming, are questions that would require detailed climate modeling to even begin to answer. What we can say is that the hydrological cycle would be more energetic. More water would be cycling between ocean, atmosphere, and land. The weather would be more intense. Storms would be more powerful, driven by the increased energy available from warmer oceans and more vigorous atmospheric dynamics. The intertidal zone, where so much of Earth's coastal ecology currently lives, would be vastly expanded in area but would also be far more violently dynamic, with tidal surges of extraordinary power regularly sweeping across coastal areas. The coastal ecosystems that currently support enormous biological productivity and biodiversity would be radically transformed. Interestingly, the increased mixing of the oceans might have some beneficial effects for certain types of marine life. Phytoplankton, the microscopic photosynthetic organisms that form the base of the marine food web and produce roughly half of Earth's oxygen, depend on nutrient upwelling from the deep ocean. Currently, nutrient upwelling is driven by temperature differences and wind-driven circulation. In a Mars-Moon world, the dramatically more powerful tidal mixing would drive much more vigorous upwelling of nutrient-rich deep water. In the short term, this might actually cause explosive blooms of phytoplankton in many ocean areas. The ocean might be more productive in some sense, even as the devastation of coastal ecosystems and the disruption of ocean circulation created other problems. Life is complex. Not everything about the Mars-Moon world would be unambiguously worse for every form of life. Different conditions produce different winners and losers. Now let's think about the relationship between this thought experiment and the actual future of the Earth-Moon system. Because here is something that is scientifically real and genuinely mind-blowing. The current Earth-Moon system is not static. It is dynamic. And its future holds some dramatic changes that, while occurring on timescales far beyond human experience, are as certain as the laws of physics themselves. As we've discussed, the Moon is gradually moving away from Earth due to tidal friction. It is currently receding at a rate of about 3.8 centimeters per year. This has been directly measured using laser ranging, where astronomers bounce laser beams off retroreflectors left on the lunar surface by the Apollo astronauts and measure the time it takes for the light to return. The current rate of recession is well established. If the Moon continues to recede at roughly this rate, in approximately 500 million years, it will be far enough away that total solar eclipses will no longer be possible, because the Moon will be too small in angular diameter to completely cover the Sun. We are, in fact, living in a very special time in Earth's history when total solar eclipses are possible. In the deep past, when the Moon was closer, it would have covered more of the sky than the Sun. In the distant future, it will be too small to cover the Sun at all. The current near-perfect match between the Moon's and Sun's angular sizes is a genuinely extraordinary temporal coincidence. Even further in the future, if the Sun were not expected to expand into a red giant and destroy the inner solar system in about 5 billion years, the Moon would eventually reach an orbital distance where it is no longer being pushed outward by tidal friction, because Earth's rotation would eventually slow to the point of synchronization with the Moon's orbit. At that point, Earth and the Moon would be mutually tidally locked, both showing the same face to each other eternally, orbiting each other with a period of about 47 current Earth days. But of course, long before that happens, the Sun will engulf the inner solar system, and this particular dance will end. In the context of this knowledge, our thought experiment becomes even more poignant. The current Earth-Moon relationship is not eternal. It is a passing configuration, a specific moment in a long dynamic history. The Moon was once much closer to Earth, making its tidal influence more like the Mars-Moon scenario we've been exploring. Early in Earth's history, perhaps 1 to 2 billion years after the Moon's formation, the Moon may have been as close as 200,000 kilometers or less, with correspondingly more powerful tidal influences. The ocean tides in early Earth's history would have been dramatically stronger than today's, though probably not as extreme as the 9 times stronger scenario we've been examining. The early Earth, under the influence of a closer, younger Moon, was a place of dramatic geological and oceanographic activity. And life still arose. Life still thrived, in its early microbial form. Life adapted to the conditions it found. As the Moon has gradually receded and the tides have moderated, life has adapted to the new conditions too, becoming more complex, more diverse, more delicately organized in the relatively stable environment that the moon's current distance provides. This long view, this appreciation of the dynamic history of the Earth-Moon system, is one of the most valuable insights that our thought experiment can offer. The world we live in today, with its particular tidal regimes, its particular day length, its particular axial tilt, is the result of billions of years of dynamic evolution of the Earth-Moon system. Our moon is not fixed in place. It has moved, it is moving, and it will continue to move. The specific conditions that make Earth hospitable to complex life today are the product of that long history, and they are contingent. They could have been different. They will be different in the future. The thought experiment of replacing the moon with Mars is, in a sense, an extreme version of asking what Earth would be like with a different moon history. And the answer, as we've seen, is very different indeed. Let's talk about the psychological experience of living under a Martian moon in more depth, because this is something that deserves more attention than it usually gets in discussions of this scenario. The human relationship with the sky is deep and ancient. We are animals that evolved under a specific sky, with specific celestial rhythms, and our psychology reflects that evolutionary history. The moon has been a constant psychological companion to our species for as long as we have been a species. Our earliest ancestors, hundreds of thousands of years ago, looked up and saw it. Our species developed language and art and religion partly under its influence. The lunar cycle is embedded in our cultural DNA. The sudden replacement of the moon with a vastly larger, red planet would be an event of profound psychological as well as physical consequence. Beyond the immediate terror of the catastrophic physical events, the more subtle long-term psychological effects would be pervasive. The sense of the uncanny, the feeling that the world had become alien and strange and threatening, would be a feature of daily life. Looking up at the sky would be an experience of awe mixed with dread every single night, for every human being alive. The familiar had been replaced by the overwhelming, by something that communicated through its sheer size the insignificance of human concerns. There is a concept in psychology and aesthetics called the sublime, the experience of something so vast and powerful and overwhelming that it inspires simultaneously awe and a kind of pleasurable terror. The natural sublime, mountains, oceans, storms, the night sky, has been a central concept in human aesthetics since at least the 18th century. The philosopher Edmund Burke wrote about the sublime in 1757, arguing that our experience of the vast and the terrible is the source of the strongest emotion the mind is capable of feeling. Under a Mars-Moon sky, the sublime would be an inescapable feature of daily life. Every night would be a confrontation with something enormous and alien and beautiful and threatening. The human psyche, shaped by millions of years of evolution and thousands of years of culture, would be in uncharted territory. Would humans adapt psychologically? Almost certainly yes, because psychological adaptation is one of our most fundamental capacities. People adapt to the most extreme and unusual environments, from the permanent night of polar winters to the claustrophobic darkness of mines to the disorienting weightlessness of orbital space. But the adaptation would take time, and the transitional period would be extraordinarily difficult for many people. Rates of anxiety, depression, and existential crisis would likely be very high in the immediate aftermath of the replacement event. The loss of the familiar moon, combined with the catastrophic physical consequences of the replacement, would create a global psychological crisis alongside the physical one. In time, however, new mythologies and cultural frameworks would develop around the Mars moon. New stories about the red companion in the sky would emerge. New religions, new art forms, new philosophical traditions would be born from the experience of living under this overwhelming red presence. The rust-colored light of Mars moon on snow or water or stone would be a new aesthetic experience that artists would explore. The vast, complex cloud patterns visible on Mars through clear sky nights, the polar ice caps going through their own seasonal cycle, the enormous shadow of Olympus Mons visible on Mars's surface as a slight darkening near one edge of the disk, all of these would become familiar features of the sky that people would paint and photograph and write about and dream about. The exploration of Mars, which in this scenario would be accessible in days rather than months, would become perhaps the central project of human civilization. There would be a Mars frontier, the way the American West was a frontier in the 19th century, or Antarctica has been a scientific frontier in the 20th and 21st centuries. People would go to Mars, would live there, would struggle to survive there, would perhaps discover extraordinary things there. The story of humanity in a Mars-Moon world would be fundamentally shaped by the proximity of another world, by the constant awareness that just a few days' journey overhead there was another place, another set of possibilities, another dimension to the human story. And what would that Mars be like to visit? This is where our scenario gets genuinely interesting, because the Mars that humans would be visiting in this hypothetical world would not be the frigid, dry, thin-aired Mars of our actual solar system. It would be a Mars that has been tidally heated by Earth's gravity, a Mars whose geology might be more active, whose subsurface might be warmer, whose volcanic outgassing might be building a slightly denser atmosphere over time. Not Earth-like by any means, but perhaps somewhat more hospitable than the real Mars. There might be geothermal features, warm springs or vents, where heat from the tidally active interior leaked to the surface. These geothermal features, if they existed, would be among the most likely places to find any Martian life that might exist, and they would also be among the most potentially valuable habitats for early human explorers, who could use the geothermal heat for energy and possibly for warmth. The view from the Martian surface in this scenario would be extraordinary, as we've already noted. Earth dominating the sky, blue and cloud-swirled, changing phases over the course of the month. Phobos and Deimos, the two real moons of Mars, which are tiny, irregularly shaped bodies with diameters of about 22 and 12 kilometers respectively, would still be in orbit around Mars. From Mars's surface, Phobos would appear as a small disk moving rapidly across the sky, orbiting Mars in about 7.5 hours, faster than Mars rotates, meaning it would rise in the west and set in the east from a Martian observer's perspective. Deimos would appear as a star-like point of light, barely resolved as a disk. And overhead, Earth would hang large and blue, perhaps the most emotional sight in all of human exploration. Home, visible in detail, hanging in the Martian sky like a benediction. Let's think about one more profound aspect of this thought experiment: what it tells us about the Fermi paradox. The Fermi paradox is the apparent contradiction between the high estimated probability of extraterrestrial civilizations and the complete lack of evidence for them. If the universe is so large, so old, and has so many stars with planets, why haven't we heard from anyone? Why are we apparently alone? One of the proposed resolutions to the Fermi paradox is the rare Earth hypothesis, developed by geologist Peter Ward and astronomer Joe Kirschvink. The rare Earth hypothesis proposes that complex animal life is extraordinarily rare in the universe because it requires a very specific set of conditions, including a star of the right type, a planet in the habitable zone, a large stabilizing moon, plate tectonics, a magnetic field, a Jupiter-like planet in the outer solar system to deflect comets, and many other factors. Most of these factors must occur simultaneously and persist for billions of years. The probability of all of them occurring together, the argument goes, is very low. If the rare Earth hypothesis is correct, Earth might be one of a very small number of planets in the observable universe with complex animal life. We might be, if not unique, then extraordinarily rare. Our thought experiment with Mars's moon provides a vivid illustration of one of the key requirements in the rare Earth hypothesis: the need for the right kind of moon. We've seen in detail what having a too large moon would do to Earth. It would not necessarily prevent life, but it would dramatically alter the conditions for life in ways that might prevent the development of complex, stable biospheres. The specific size and distance of our moon is not just a lucky coincidence. It might be a necessary condition for the kind of stable, long-term habitability that allows complex life to evolve over billions of years. The Fermi paradox remains unresolved. But thought experiments like this one help us understand why the universe might be quieter than optimistic estimates suggest. Complex life might require not just a habitable zone planet, but a habitable zone planet with a right moon, and that specific right moon might be rare enough that civilizations capable of radio communication might be extraordinarily sparse even in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars. Now let's consider the question from a completely different angle, one that people rarely think about. What would this scenario mean for the study of Mars itself? Because right now, in the real world, Mars is one of the most intensively studied objects in the solar system precisely because of our desire to understand its history and to search for life. Multiple spacecraft orbit Mars currently. Rovers explore its surface. Plans are underway for human missions in the coming decades. If Mars were orbiting Earth at the distance of our moon, the nature of our scientific relationship with Mars would be transformed. The detailed pixel-level imagery of the entire Martian surface that we have painstakingly built up over decades of orbital missions would be available to any amateur with a good backyard telescope. The question of whether Mars has life would be answerable not over decades of expensive robotic missions, but over a much shorter timescale of direct exploration. The sample return from Mars, which in real life is a complex, multi-billion-dollar mission currently under development, would be a routine activity. Understanding Mars completely would be within reach of human civilization in a matter of decades rather than centuries. And what would we find? This is the question that haunts all Mars science. The current evidence suggests Mars once had liquid water, that Mars once had a denser atmosphere, that Mars may have been habitable to life billions of years ago. Whether it actually had life, and whether any remnant of that life persists today in protected subsurface niches, is unknown. The discovery of even microbial life on Mars would be the most profound scientific discovery in human history, transforming our understanding of life's ubiquity in the universe and answering one of the oldest and deepest questions. Are we alone? In our hypothetical scenario, with Mars at lunar distance, this question would be answerable much sooner and with much greater certainty than in our current situation. The possibility of discovering that Mars was once alive, or still is alive in some form, would be the silver lining in an otherwise catastrophic scenario. Amid all the destruction and chaos caused by the replacement, the discovery that life exists beyond Earth, that the universe is not an infinite, sterile void punctuated by rare islands of biology, would be a revelation of incomprehensible importance. It would reorder human philosophy, religion, and science. It would tell us that life is not an accident, not a unique miracle of one planet, but a feature of the universe, something that arises wherever conditions permit. And that knowledge, however it arrived, however dramatic and traumatic the circumstances of its discovery, would change everything. We've spent a long time exploring the immediate and medium-term consequences of our thought experiment. Let's now take a long view and think about what Earth would look like a billion years after the replacement. Assuming the system remained stable and life somehow survived and evolved in the new conditions. A billion years is a time frame that taxes human imagination. It's roughly 20% of the age of the universe. It's the time frame over which major evolutionary transitions occur in biology, over which plate tectonic cycles reshape entire continental arrangements, over which the gradual brightening of the sun changes the energy input to Earth's climate system. In a billion years with a Mars-Moon, Earth's rotation would have slowed significantly due to the greatly amplified tidal braking. The days would be much longer, perhaps the length of a current week, or more. The tidal forces, while still powerful, would have diminished somewhat as Mars slowly moved outward in response to the tidal angular momentum transfer. Life, whatever forms it had taken in the intervening billion years, would have adapted to longer days, more extreme tides relative to our current baseline, but perhaps less extreme than the immediate aftermath of the replacement, and a dramatically different tectonic and oceanographic environment. The planet's surface would look different. The continents would have moved, as they always do due to plate tectonics. The ocean basins would have different shapes. The climate, driven by the same solar energy but differently distributed by altered ocean circulation and different atmospheric composition resulting from a billion years of altered geological activity, would be different in ways we cannot specifically predict. But life, almost certainly, would still be there. Adapted, diversified, shaped by a billion years of selection in the new environment. Whether anything like complex animal life, let alone intelligent life, would have emerged in this environment is unknowable. But the principle that life adapts and persists and diversifies is one of the most robust conclusions of 4 billion years of biological history on Earth. and there is no compelling reason to think it would be violated under even the dramatically altered conditions of a Mars-Moon world. The relationship between Earth life and Mars, at this point in our hypothetical timeline, might be complex and intimate. Billions of years of material exchange between the two worlds, accelerated by the proximity of Mars and the geological activity of both worlds, might have resulted in a shared biosphere of extraordinary complexity. Life from Earth might have colonized Mars. Life from Mars, if it originally existed, might have infused Earth's biosphere with novel chemistry. The two worlds might, in a sense, be partners in the story of life in this region of the solar system, each shaping the other's biological evolution through the constant exchange of material and the shared gravitational environment. In a strange way, this long-term vision is perhaps the most optimistic conclusion of our entire thought experiment. In the midst of all the catastrophe and chaos of the initial replacement, in the face of the devastating tidal floods, the earthquakes, the volcanic eruptions, the climate disruption, the social and psychological collapse, life would persist. Life would adapt. And over geological time, life might produce a world of extraordinary biological richness and complexity, perhaps even more complex and interconnected than what Earth harbors today, born from the creative crucible of two worlds in intimate gravitational conversation. This is not to minimize the catastrophe. The immediate consequences would be horrific. Billions of people and trillions of other organisms would die. The comfortable, organized world of human civilization would be shattered. But life's story on Earth has been punctuated by catastrophe before. The planet has survived impacts, ice ages, massive volcanism, and ocean anoxic events. Each catastrophe has been followed, eventually, by recovery and renewal. The Mars-Moon catastrophe would be in the top tier of such events, but it would not necessarily be the end of life's story on Earth. Just a very dramatic chapter break. Now, here's something I want you to sit with as we begin to draw this exploration toward its close. Every single calculation we've been through, every single physical consequence we've described, every tidal force and gravitational interaction and atmospheric effect, all of it follows from the same basic principles that Newton described in the 17th century. The inverse square law of gravitation, the conservation of angular momentum, the mathematics of orbital mechanics. These are not exotic or uncertain ideas. They are among the most thoroughly tested and verified concepts in all of science. The simple act of changing one number, the mass of Earth's moon, by a factor of 9, produces consequences so dramatic and so all-encompassing that it transforms a habitable, stable, biologically rich world into something barely recognizable. The fragility of our world, the delicate balance of conditions that makes life possible here, is made vivid and immediate by thinking about what just one change would do. And the particular change we've been exploring, replacing our moon with Mars, is not random. It's connected to the real history of the solar system. The moon was formed from a Mars-sized impact. Mars itself is the remaining representative of the class of bodies that shaped the early solar system. The moon we have is a direct consequence of the Mars-sized body that it was not. And in some cosmic sense, the world we live in, the world that has produced life and consciousness and science and art and music and all the complexity of human civilization, is exactly the world that resulted from Mars not being our moon. We are here because of what didn't happen. We are here because Theia hit Earth and scattered into the moon rather than staying whole and orbiting. We are here because the dice of the early solar system rolled in a particular way, and the consequences of that roll have been playing out for 4.5 billion years in the form of life, increasingly complex life, and eventually conscious, curious, questioning life that sits here asking what if the moon were Mars. There's something humbling and something exhilarating in that. The universe is not designed for us. It does not care about our survival or our flourishing. The conditions that make life possible are contingent, the result of specific historical events in the early solar system that could easily have been different. And they very nearly were. Mars-sized bodies were common in the early solar system. The fact that one of them hit Earth and formed the moon rather than remaining as a separate body is a specific historical fact about our specific solar system. In other solar systems, in other planetary configurations, the dice rolled differently. And the consequences are different in ways that we can, with some effort and some physics and some imagination, begin to understand. This is what the question, what if the moon was replaced by Mars, ultimately gives us. Not just a dramatic thought experiment about tides and earthquakes and red skies, but a window into the contingency of our own existence, into the specific set of cosmic accidents that produced a world capable of supporting life like us.